Welcome back to G Fun Facts Online, where we dive deep into the science and technology shaping our future. Today, we are going to talk about a problem that is arguably the hottest issue in climate change, quite literally, and the solution that might just be sitting in a kiln from the Bronze Age, reinvented for the 21st century. When we think about climate change, the mental images are almost always the same. We picture tailpipes on the highway, or giant smokestacks attached to coal power plants. We imagine a future where electric cars replace gas guzzlers and solar panels replace coal. And while those are crucial pieces of the puzzle, there is a massive, invisible sector of the energy economy that those solutions barely touch. We are talking about industrial process heat. This is the invisible furnace that builds our world, making the steel for your car, the cement for your driveway, and the glass for the smartphone you are holding right now requires temperatures that are mind-boggling. We are talking about heat that would melt a standard heating element in seconds. For over a century, the only reliable way to generate this 1500 degrees Celsius plus heat was to burn something, usually coal or natural gas. This specific slice of the energy market is called thermal reliance, and it accounts for roughly 20% of global greenhouse gas emissions. That is a stubborn wedge of the carbon pie that batteries and wind turbines have really struggled to cut into. But that is changing. A Boston-based startup called Electrified Thermal Solutions, or ETS, has reinvented one of humanity's oldest technologies, the firebrick, to solve this modern crisis. Their solution is called the Joule Hive, and it is a thermal battery that doesn't just store heat, it generates it, turning intermittent renewable electricity into a reliable, flame-temperature inferno that can run heavy industry 24/7. To really appreciate why this is such a breakthrough, we first need to do a bit of physics. We need to understand the limits of a toaster. Most electric heating we use in our daily lives works on the same principle as a toaster or a hairdryer. You pass electricity through a metal wire. The wire resists the flow of electricity, and that resistance creates heat. This is fantastic for making toast at 200 degrees Celsius. But if you try to heat a steel blast furnace to 1600 degrees Celsius using metal wires, you hit a physical wall. The wires themselves will soften, oxidize, and eventually melt or snap. You essentially cannot heat a kiln to temperatures hotter than the heating element itself. This physical limit has been the Great Wall blocking the electrification of heavy industry for decades. This is where ETS comes in. Spun out of MIT's Department of Nuclear Science and Engineering, the team, led by Dr. Daniel Stack and Joey Cabell, found a way to bypass the wire entirely. They developed something called the E-brick, which stands for Electrically Conductive Firebrick. Now, standard ceramic bricks are excellent electrical insulators. That is usually why we use them. They stop electricity, but ETS realized that if they doped these bricks with specific metal oxides, like adding small amounts of nickel to chromium-based ceramics, they could change the material's properties at the atomic level. This doping process creates defects in the atomic lattice of the ceramic. These defects act like stepping stones, allowing electrons to hop from atom to atom. This phenomenon turns the brick itself into a resistor. So when you plug a Joule Hive into the grid, electricity flows directly through the stack of bricks. The bricks themselves become the heating element. Because they are made of refractory ceramic materials designed to withstand extreme environments, they can safely reach temperatures of 1800 degrees Celsius, or nearly 3300 degrees Fahrenheit. That is hotter than the melting point of steel and hot enough for virtually any industrial process. This brings us to the system itself, the Joule Hive. It is often described deceptively simply as a box of hot rocks, but the engineering is precise. It operates in 3 phases. First is charging, or joule heating. During periods when electricity is cheap, like midday when solar power is peaking or windy nights, the system draws power from the grid. This electricity passes through the E-bricks, which heat up via resistive heating with 100% efficiency. The second phase is storage. These E-bricks are stacked inside a heavily insulated steel container. This thermal mass acts just like a battery, holding its temperature for hours or even days, with minimal energy loss. It effectively time-shifts renewable energy, capturing it when it is available and storing it until the factory needs it. Finally, there is discharging. When the factory needs heat, air, or another gas is blown through channels engineered into the brick stack. The gas absorbs that intense heat and exits the hive at the precise temperature required by the facility, whether that is 300 degrees for drying food or 1600 degrees for making cement clinker. This turns a variable input, like wind or solar, into a constant output of industrial heat. Now, ETS isn't the only company trying to solve this. The thermal battery landscape is heating up, pun intended. You have companies like Rondo Energy, who are using a toaster approach. They use conventional heating elements, those metal wires we talked about, to radiate heat into standard firebricks. It is effective and simple, but it is generally limited to temperatures around 1500 degrees because of the constraints of the heating element. Then you have Antora Energy. They use solid carbon blocks heated to over 2000 degrees. Carbon is cheap and heat resistant, but there is a catch. Carbon burns if it touches air at those temperatures. So Antora's system requires an inert atmosphere, usually argon gas, to prevent the blocks from oxidizing. ETS and the Joule Hive occupy a unique niche between these two. Because their conductive ceramics are oxide-based, they cannot burn, they are already oxidized. This means the Joule Hive can operate in standard ambient air. This air-breathing capability is a massive advantage because it eliminates the need for complex inert gas systems or vacuum seals. It makes the Joule Hive a drop-in replacement for gas boilers and kilns that already use air intake systems. This technology is moving rapidly from the lab to the real world. ETS has secured major partnerships to prove this works at scale. Let's look at their project with Ashland, a global additives and specialty ingredients company. Funded partly by the U.S. Department of Energy, this pilot involves replacing natural gas-fired boilers at Ashland's plant in Calvert City, Kentucky. The Joule Hive will generate steam for the plant's operations. The impact of this single project is staggering. It is projected to reduce CO2 emissions associated with steam generation at the site by nearly 70%. That eliminates roughly 72,000 tons of CO2 per year. To put that in perspective, that is equivalent to taking over 15,000 cars off the road, just from upgrading one part of one factory. Then there is the cement industry, which is notoriously difficult to decarbonize. Making cement clinker requires consistent heat around 1450 degrees Celsius. ETS has partnered with Biza Unisum USA and the Southwest Research Institute to build a commercial-scale pilot in San Antonio, Texas. If this works, it could prove that electric heat can replace the massive coal and gas kilns used in cement production, unlocking a path to net zero concrete. And we cannot forget steel. In September 2024, steel giant ArcelorMittal invested in ETS through its XCarb Innovation Fund. The steel industry is desperate for ways to move beyond coal-fired blast furnaces. While hydrogen is often touted as the solution, it is currently expensive and inefficient to transport. Direct electrification via the Joule Hive offers a compelling alternative for heating processes like reheating furnaces and potentially even primary iron making. But the rise of Joule Hives isn't just about physics, it is about economics. The energy market is changing. We have something called the duck curve. As solar power saturates the grid, electricity prices often plummet to near zero, or even negative, during the middle of the day. Industrial plants using gas boilers can't take advantage of this because they can't easily switch fuel sources. A Joule Hive, however, loves this volatility. It can gorge on cheap electricity for 4 hours during the solar peak and slowly release that heat over the next 20 hours. It effectively arbitrages the electricity market, buying low and selling high, or rather, using high-value heat. The policy wins are also filling these sales. The U.S. Inflation Reduction Act has been a game-changer. Specifically, the Section 48C investment tax credit provides a credit of up to 30% for advanced energy manufacturing projects. Furthermore, the Department of Energy's Industrial Heat Shot Initiative has set a target to reduce emissions from industrial heating by 85% by 2035. This creates a massive government push for technologies exactly like the Joule Hive. In a poetic twist, the solution to our most futuristic energy problem lies in one of our oldest materials. Firebricks have lined kilns since the Bronze Age. By tweaking their atomic structure to conduct electricity, Electrified Thermal Solutions has bridged the gap between the ancient and the modern. The challenge ahead is scaling. The industrial heat market is massive, double the size of the global electricity market. To make a dent, ETS will need to deploy gigawatts of capacity, but they have a few aces up their sleeve. They use no exotic materials. Nickel and chrome are abundant. There are no rare earth supply chains to worry about, and the modular design fits into shipping containers. We are standing on the precipice of a new industrial revolution, one where the blast furnaces are silent, smokeless, and powered by the sun. It is a fascinating time for energy technology, and the e-brick might just be the foundation of a cleaner, heavy industry. Thanks for listening to this deep dive on G Fun Facts Online. We will catch you in the next episode.